Everything is clear, beta? Audio and video, everything? Please respond in the chat box if it is clear. So, my dear, today we will discuss of the problem, previous year problem related to 21, and also will be cover for that one. That means what we have to cover? We have to cover all the entire questions of a turbo machinery. Why? Because we know that in the turbo machinery, a little bit there is a problem there in the student community. So we will try to resolve, and also we have to try to fix this problem and minimize maximum to maximum at a given time of a span. So what we have to analyze that means beta, see in turbo machinery there are two type of turbine. First turbine is the impulse turbine, second one is the reaction turbine. Okay, so in the case of impulse turbine, the flow of a fluid is the tangent of the rotor. You can say that tangent. Why? Because in the turbine there is a rotor, in the pump there is an impeller. So the name is differ. The name is very clear. In the case of a turbine, the rotating part is called rotor, and in the case of pump, the rotating part is called impeller. Okay, now my dear, if you talk about only turbine, why? Because in the GATE syllabus we have only turbine is there. So in the turbine there are two type of turbine. First is impulse turbine and second one is reaction turbine. So in the impulse turbine, the flow of the fluid is the tangent of the rotor, and in the case of reaction turbine, the fluid flow throughout the rotor is in two form. First, it is in axially, pure axial, that is called propeller, or that is a propeller turbine. You can say the propeller or a Kaplan turbine. And the second one is that the flow is a radial or a mix, that means radial plus axial, that is called Francis turbine. So the name, it is clear for a three category. First is the Pelton turbine, second one is the called Francis turbine, and third one is called the propeller turbine or a Kaplan turbine. Okay, so my dear, if you talk about the first question asked in 2021, there is a Pelton turbine. So very clearly you have to see that from the jet, you know that from the jet the fluid is ensuing, and that high kinetic of the fluid will be strike on the series of the plate. That plate is mounted on the wheel, that is called Pelton turbine. And so that this Pelton turbine will run with some RPM, that is given 300 RPM. The mean diameter of the wheel, that means a wheel have a diameter, so we have to calculate the diameter at a mean basis, or simply we call that a diameter of the wheel is 2 meter. The operating head, that means the turbine will be operate at some height, some head. So operating head and the dimension of the jet in such that water coming out of the jet with a velocity of 4 meter per second. That means what is the entry velocity of the fluid in the turbine is 40 meter per second, and the flow rate, that means the discharge, is 5 meter cube per second. Okay, now the jet is deflected by the bucket. That means if the jet will strike, that jet will deflected at an angle of 165 degree. That is deflection angle. Neglecting all the losses, the power developed by the Pelton wheel. This is the very basic question. If you in the turbo machinery subject, so such type of question, it is called a very basic question. So what is that? We have a we have a this type of all the arrangement. That means, see very clearly, there is a wheel is that, okay, and that wheel, on the wheel there are a there are a series of the bucket called blade is there, okay. If we rotate this wheel, let's suppose the jet will strike, and the jet velocity it is given, and the jet will strike will be tangent to the wheel. That means this jet, the direction of the jet velocity is the tangent to the wheel. That is called, that is this Pelton turbine is a tangential flow turbine. So what is the in velocity is same as the out velocity radial distance. That means the rotor velocity at inlet to the jet and the rotor velocity when the fluid is exit from the jet, these have a same radius. So the rotor speed, that means the tangential speed of the rotor, let's suppose it will move omega. So the u is equal to r into omega. So this u is the tangential velocity of the rotor, and r will be measured from the center of the wheel to the mean radius of the bucket. So this is your mean radius. This is called mean radius or a mean diameter. That means this velocity, that means in the Pelton turbine, what is the inlet velocity? Same as the exit velocity. Why? Because, see my dear, the jet will coming and the same axis, that means same axis the jet will deflect. That means the plane is same. That means the jet will move entry at the some location of R1 and exit at a location R2, but if the fluid is tangential, that means this is the shaft and this the fluid is tangential, so what is the radius from the shaft at inlet and radius from the shaft at exit? Both are same. Why? Because it is tangential. Okay, now this is the bucket shape. What is that bucket shape? Is there is a splitter is there. So if jet will strike, let's suppose the jet will strike at this point of a dia D. Let's suppose this is jet dia, and this diameter of the jet, this jet will be glide on the curve of the blade, and this will, this is like that. See, this is like that. The jet will into the blade and it will glide like that. That means it is in and it will glide like that. It is not that it is in and it will glide like, no. The gliding is the same level of that horizontal plane of the horizontal axis of the shaft. So this is your, the part which is split the jet into the parts, that is called splitter. And this is the blade velocity. That means if the velocity V1, that V1 velocity is inlet to the nozzle, that velocity V1 will be strike on that. This is the, if this is your front view, this is your front view. If we will take rotate one at 90 degrees, so this is your edge view. So this hatched part is your blade. Now the velocity will enter. Which velocity? V1 velocity. V1 velocity is what velocity? Velocity at velocity of the jet which is in swing from the nozzle. So this velocity is coming. It is not like that vertically outward and vertically outward. No, it is the same plane in a horizontal plane. That means the jet will strike and this will glide in the two parts. So it will in and it will glide over the blade. It will glide over the blade. That gliding is there so that it will move. So this is your V1 velocity is into the blade, and there is a velocity which is a relative velocity known as VR2. That means this velocity is velocity with respect. This velocity is the velocity of water. This is also velocity of the water, but this velocity of the water which is with respect to the nozzle, and the nozzle is fixed, so this is called absolute velocity. Nozzle is fixed, so this is called absolute velocity. Now after striking this water, this will after striking this water on the blade, it will split into two parts and then it will exit with respect to the blade velocity. That is called relative velocity. That is called relative velocity. So this is your bucket, so that the blade will move. So this u velocity is the same as u1 equal to u2. And what is the u velocity? Is the tangential velocity. So this is called tangential velocity, a blade velocity. Blade velocity. This is called blade velocity. This is called blade velocity. Now, so if you draw the inlet and exit triangle, so beta, if we take, this is your in and this is your exit, so in it is in a straight line. In it is a straight line. So this line, let's suppose the line from here to here, the velocity is v1. Now this velocity v1 is the vector addition of peripheral velocity of the blade plus the relative velocity. Always remember, the absolute velocity is a resultant velocity. The absolute, that means v1 velocity is a v1 yeah v2 velocity is a resultant velocity of a u and vr. So u it is in this direction, vr it is in this direction. So in this case of a Pelton turbine, the v1 velocity which is ensuing from the nozzle, it is equal to the peripheral velocity plus the relative velocity at inlet. That's it. This is your velocity at the entry to the nozzle. Now, so this is inlet. Now, if we take the exit triangle, so from here, the velocity is out. Which velocity out? VR2. So, the VR2 velocity is out. Let's suppose this VR2 velocity is out. Now, my dear, see, if we draw the triangle, at this point, let's suppose if you draw the triangle, okay, so at that point, this velocity, let's suppose this velocity is VR2. Okay, this velocity is VR2. So, beta, U and VR relative velocity have a same sense. Sense is same sense. That means it will be same sense and opposite sense of a resultant. We know that if there is a two vector and if you find the resultant is always opposite sense of the two vector. So this is your VR and this is your U. So VR and U are the same sense, see, and this is your velocity V2, opposite sense. So this is your resultant velocity. See this one. This is your V, this is your U, blade velocity, and this is your relative velocity, and the resultant is your V2 velocity. Resultant, it is your V2 velocity. The V2 velocity, that means absolute velocity, have a further component. What is the component? One is the whirl component, the other one is the flow component. Flow component. So whirl component, whirl velocity, that means this is a velocity of whirl which is responsible to rotate the blade. And this is the responsible to flow the fluid. So if we calculate the discharge, we have to calculate the flow velocity. So this is your V2. This V2 have a horizontal component, it is in VW2, and this V2 have a vertical component is equal to VF2. VF2. So we have to make a triangle. And if there is a loss there is a friction loss, so the K is the factor, and this is the ratio of relative velocity at outlet divided by relative velocity at inlet. So if you know how much the loss is there, multiply with the relative velocity V1, you have to get the relative velocity at the exit. So this is this depends, we have to detail in the class, this K is the factor which depends upon the two factor. First is due to the friction and second is due to the angle deflection. Clear? So it is not that if there is a smooth friction, so K is 1. No, it may be a deflection. So this will depends not only due to the friction. Okay, we already discussed in the detailed class. Okay, now my dear, if you solve this problem, we have to design a inlet and exit velocity triangle. Now my dear, this inlet velocity is fixed. Inlet velocity, the inlet velocity, see this one, inlet velocity triangle is fixed. Why? Because it is in a straight line. But exit may be changed. How at which condition the exit velocity will change? We have to discuss in detail. Why? Because there is a large mistake, huge mistake in the student community. Ki sir, how to draw the exit velocity? Why? Because inlet velocity you have to draw. The total length of the line is the V1 vector, split into two parts, U and VR1. That's it. But once you have to draw the exit velocity triangle, it's have a difficulty. Ki sir, how to draw? How to manage? Why? Because there may be three possibility. There may be more than one possibility of to exit velocity triangle. So which we have to fix the correct velocity triangle. So we will discuss about this thing. See, my dear. Okay. Now, if we draw, okay. Now, my dear, so this is a given. What is that? See. 1 second. We have to fix all this thing. No problem at all. So, this is your inlet velocity. See this one. You have to draw the inlet velocity triangle. This is your inlet velocity. It is in a straight line. Okay. This is your inlet velocity. Okay. No problem at all. This magnitude is your V1. This magnitude, it is your V1. Total magnitude, it is your V1. So from here to here, this velocity is V1. This velocity, it is the velocity which is in swing from the nozzle. And nozzle, it is fixed. In the case of a Pelton turbine, in the case of the Pelton, yes, Pelton wheel turbine, yeah, impulse turbine, this V1 velocity is your fixed velocity. Now, we have to split it into the two parts. This velocity part, let's suppose this is your U, is the peripheral velocity, and this is your relative velocity VR1. So, inlet velocity triangle is fixed. No problem at all. Now, what is the exit velocity triangle? So, exit velocity triangle, let's suppose, beta, exit velocity triangle we have to draw. Exit velocity triangle we have to draw. So, first we have to draw this shape like that, okay? This is not in a vertical plane. This is not in a vertical plane, this is a horizontal plane. So, here inlet is there, and from here the exit velocity. So, fluid will into this one, fluid will entry into this one, entry into this one, entry into this one, and it will exit. So, it will exit like that. So, this is the velocity, your relative velocity. What is that? Relative velocity. Let's suppose this is your VR2. This velocity is your VR2. And this velocity is U, blade velocity. So, this will exit at relative velocity VR2. Now, my dear, this VR2. Now, this velocity, this is your U velocity. That means this is your, why? Because, see, if you draw this one, this is the U direction. This is the U direction, U direction, U direction. So, let's suppose this is your U velocity. Let's suppose this is your U velocity, U. U is same. Why? Because tangential, U velocity. So, U and VR2 have a same sense. U and VR2 have a same sense, and the resultant opposite sense of V2. So, this is your opposite sense. V2, V2. It is not upward, it is downward. Why? Because these two, V and U, are same sense and opposite sense of V2. Now, my dear, this V2 have a component. So, this angle, this is your V2. Now, in this one, so it is move like that, but it is not due to the blade, it will deflect. So, this angle is called deflection angle. This angle is called theta, and this is given 165 degree. This is called one second. This is called 165 degree. It is given. So, this is how much the angle it is. This is called outlet blade angle beta 2. and this is your beta 2. So what is the beta 2? Beta 2, that means blade at exit is 180 minus 165. How much it is? It is approximately beta 2 is 15 degree. Okay, so deflection it is in 15 degree. Now if you take this V2 component in a vertical direction, in this direction, this is your V2 component, this is called VF2. And if you take this V2, it is in horizontal component, this component, this is your V2, so this is your VW2. So this V2 have a two component, vertical component and horizontal component. So this is your horizontal component, this is your vertical component. Okay, now this is your diagram, and beta, if there is a loss is there K, so what is you have to K? VR2 is equal to VR divided by VR1. So what is VR2? VR2 is equal to K of VR1. If the K it is negligible, so what is the relative velocity at exit? The same relative velocity at inlet. So this V2 we have to write like that, K of VR1. K of VR1. Okay. Now my dear, what now first we have to find what is this U. So U is what beta? Bucket speed. Bucket speed. Bucket speed is same at inlet and exit of the water jet, Why? Why? Because flow is tangential. Tangential flow. That means if this is your shaft, let's suppose. So if this is your shaft, let's suppose this is your, 1 second, I'm coming. Let's suppose this is your shaft, right? So this shaft, it is like that, okay? See this one. This is like that, okay? This is your shaft. Now, this shaft, on this shaft, my dear, there is a rotor is there. Okay, this shaft, there is a rotor is there. Now, the fluid, how the fluid is flowing? The fluid is flowing from at, see, this is the blade is there. This is the bucket is there. This is the bucket. So let's suppose this is the bucket. At downside, there is a bucket. This is your bucket. So at this point, the fluid is entry. At this point, the fluid is entry, and at this situation, the fluid will enter, and it will split into two parts. So what is the distance from the center of the shaft at inlet? Same radial distance at exit. So the velocity u1 equal to u2 in the case of tangential flow. So this is your shaft. If there is a tangential flow, that means this will try to rotate. This shaft will try to rotate. The flow, that means the flow, it is at inlet and at it is exit. So if the flow is tangent, so what is the center distance at inlet is the same center distance at the exit. So the velocity u1 equal to u2 is there. So in this case, my dear, in this case, the tangential flow is there. That means the blade velocity at inlet to the nozzle is the same as the blade velocity at inlet to the nozzle, exit to the nozzle, and that is your R into omega. Yeah, you can say that d by 2 diameter of the wheel into omega. So this R is not changing either at inlet section or exit section, and omega is the RPM of the speed, radian per second rotation of the speed. So this U is fixed. This U is fixed is there. Now my dear, now the N it is given. N it is in RPM, how much it is given, beta? Please tell me. N is, it is what? N it is given. N it is your 300 RPM. 300 RPM. N it is given 300 RPM. Diameter of the shaft it is given, the rotor it is given 2 meter. See the dimension, 2 meter it is there. Now, so if we calculate U velocity, what is U? Pi dn. Pi dn upon 60. So pi, what is diameter of the rotor? 2. What is N? N is the RPM. 300 divided by 60. So this out, it will 31.4 meter per second. So this 31.4 meters per second, it is at this speed, it is entry, and at this speed, it is exit. Okay, no problem at all. Now we have to take the inlet velocity triangle. If you look the inlet velocity triangle, so triangle in. So if we take the inlet velocity triangle, so what is the inlet velocity triangle? Sir, VR1 is equal to V1 minus U. Okay, and V1 it is given. V1 it is given, beta. See, it is given the water coming out of the jet with the velocity 40 meter per second. So this is your 40 meter per second. So this is your 40 meter per second minus you have just now have to calculate 31.4. How much it is? Please tell me. This is equal to 8.6 meter per second. Okay, this is your 8.6 meter per second. So this is your relative velocity. Now, my dear, here we have to neglect the losses. So if you neglect the losses, in this case, we have to neglect the losses. So this is also equal to VR2. Why? Why? Because K equal to 1. Neglect the losses. Neglect losses. We have to neglect the loss. So K equal to 1. So VR1 equal to VR2. So what is this VR2? We have indirectly, we have to find it. Now, my dear, what is our exit velocity? Now, again, we have to, if you draw anything, that means this is your velocity, which is your V1. This is your velocity, which is your V1. Clear? This is your V1. Right now, oh, it is, I think it is not in aligned manner. Okay, no problem. So this is your V velocity of, okay, right. Now, here, this is your velocity, clear? This is your velocity. Let's suppose this velocity is VR. It is like that. So, this is your, okay. Now, this is the direction of U velocity. U is there. So, this is your U. So, this is your U is there. Very good. This is your U is there in this direction. This is your U. And this is your VR2. VR2. Neglect the loss. So this is your VR1. What is VR1? We have. How much it is? 8.6 meter per second. Correct? And this angle is your beta 2. And beta 2, how much it is given, beta? Beta 2, it is given 15 degree. 15 degree. Why? Because this is your deflection 165 it is given. Clear na? This is your 165 it is given. So this is your beta 2. Now, so this is your U, this is your V. So in this direction. So it is in this direction. 1 second. So it is, this is your velocity. This is your velocity. Okay. So this is your velocity in this sense. Okay. So this is in this sense. So it is in this sense. So this is your V2. Now this V2 have a component. So this V2. So this is your beta. So this V2. Now always beta blade angle, it is the angle between the peripheral velocity to the relative velocity. Always remember. Okay. So if you take the component horizontal and vertical, if you take the component horizontal and vertical, if you take the component horizontal and vertical, okay, horizontal and vertical. So if you take this V, so my dear, if you take the component of this one, if you take the component of this one, let's suppose you have to take the component. Okay, so this component, this component, it is your perpendicular to the U, and this is along the U. This is your along the U. Okay, so along the U, that is your whirl velocity VW2, and perpendicular to the U, that is your flow velocity or axial velocity VF2. Clear? 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 Now, now if we calculate, so what is that beta? VR2 cos beta 2 from the diagram, from exit velocity triangle. What is that? VR2. Let's say that that means VR2 cos beta 2. So VR2 cos beta 2 is what? VR2 cos beta 2. So this is your VR2 cos beta 2 at this line. So this is your VR2 cos beta 2. Yes or not? Yes or not? This is your VR2 cos beta 2. Okay. So this, if you calculate this one, why? Because we have a VR2, that means 8.6 cos of 15 degree. How much it is? It is approximately 8.307 meter per second. So this is VR2 cos beta 2. Now my dear, what is U? What is U? U is equal to U1 equal to U2. How much it is? How much it is? It is your 31.4 meter per second, which is greater than VR2 cos beta 2. Let's suppose this is your X, which is greater than this value X. See the beauty. So in this triangle, the VR2 is greater than V2. Yes or not? So this diagram is wrong. You have to check like that. This X is what? VR2 cos beta 2. So VR2 cos beta 2 is less than the velocity U. That means this is the velocity U, which is less in this diagram. In this diagram is what beta? In this diagram, this velocity U2 is your less than this velocity X. Yes or not? But calculation, this X velocity is less than the velocity of U. So this diagram is wrong. Wrong diagram. So how to change this diagram? So very clearly, this velocity in this figure, this is your U velocity and this is your X, that means VR2. But in this diagram, VR2 cos beta 2 is higher than the U velocity. But if you calculate numerically, the U velocity is greater than VR2 cos beta 2. That means this diagram is wrong. So what you have to do? You have to do, that means this component, that means this component is less, so that this, why? Because VR2 cos beta 2 is what? What is the component? That means this is your VR2 component. VR2 cos beta 2 is the VR2 component along U direction. That means if you take a less magnitude of this one and if you take high magnitude of U, if you take the component, that is okay. So how to design this one? So if you draw like that, see my dear, if you draw like that, that means this is your velocity, this is your velocity, this is your velocity, okay. So this is your U velocity. Now if we'll take, this is less, this your VR2 is less, okay, this VR2 is less. So this is your VR2, this is your U, okay, this is your VR2, this is your U, and this is your beta 2. So the component of this, so what is VR2 cos beta 2? If you take the component of, so this is your U, this is your VR2, so obviously this is your V2. Obviously this is your V2. So this is your V2. This is your V2. This is your V2. Now if you take the component of this one, if you take the component of this one, if you take the component of this one, so this is your VR2 cos beta 2. This is your VR2 cos beta 2. Yes or not? VR2 cos beta 2. So in this diagram, this U velocity is greater than VR2 cos. So this diagram is okay. This is okay, and this one is okay. This one, this is your VR2, and if you take the component of this one, if you take this vertical component, not like that, if you take the component of this one in this direction, if you take the component of this one in this direction, this this is your VW2 and this is your VF2. Perpendicular to the U velocity is VF2. Okay, and this is your alpha 2. This is your 90 degree. So this diagram is okay. Now the diagram is clear. Now the diagram is clear. Which diagram you have to take? So this diagram is wrong. Why? Because if you calculate VR2 cos beta 2, that magnitude is less than the what is the velocity it is given. So but in this diagram, this magnitude is higher as compared to the velocity. So we have to take intuitionally this velocity V. Why? Because VR2 is the component of VR2. VR2 cos beta is the component of VR2. So we have to take a less magnitude. So if you take less magnitude, so obviously at this point, that means this, if you draw this line here like that, so then it is okay. So instead of this V2, we have to take this V2. So that this is your VR2. So the component of this VR2 is less than the component of this U. Clear? So this is your precisely the diagram. Now my dear, so from this diagram, if you draw this one, if you draw this diagram again, beta, so this is your U. We have to again draw, no problem. So little bit bigger. This is your U. Now it is clear. This is your U. Okay. This is your U. This diagram. This is your VR2. okay, and this is your V, and this is your perpendicular direction. If you draw this perpendicular direction, okay, this is your perpendicular direction. This angle, so if you draw that, so beta, this is your VR2 is equal to VR1, it is given. This is your beta 2, it is given. And this total distance, it is your, from here to here, this is your U. 1 is equal to U2. Okay. So this is your U direction. Now, so this is your same sense. So in this direction, this is your opposite sense. This is your V2. This is your V2. And this is angle is your alpha 2. And if you take this component, so if you take this component beta, so this is the component of your V2. This is your component of your V2. So this component of V2, this component of your V2 is called exit whirl velocity V2. And the component which is along V direction and which is along the perpendicular direction, of this one, that is called VF1. So this is your VF1, not VF1. This is your VF2, flow velocity VF2. That is okay, no problem. This is the actual diagram. This is your actual diagram. Okay, so you don't bother about sir which type of diagram. You just calculate the component of the relative velocity along the horizontal direction and compare with the blade velocity. Compare with the rotor velocity. If this component of this relative velocity along the U direction is less than this U velocity, this is the diagram. If this component of VR2 is higher than of this U velocity, so this is your diagram. Clear? Now, so what is VW2 here? VW2. What is VW2? VW2 from the figure. VW2 is equal to U2 minus VR2 cos beta 2. Yes or not? Yes or not, beta? This VW2 is your U2 minus this component. Why? Because this component is what? Okay, 1 second, we don't disturb like this one. Okay, so this is your, if you take this component, so this from this point to this point, it is your VR2 cos beta 2. So if total minus subtract this one, this is your VW2. So what is the VW2? So U2 you have 31.4 minus VR2 you have 8.6 cos of 15 degree. How much it is? So this is your 23.09 meter per second. This is your whirl velocity. Now my dear, always remember, this thing is always remember, whenever there is you have to find the power developed by the turbine. Always we have to take the velocity of a whirl velocity. Why? Because this velocity is responsible to rotate the shaft. This velocity is responsible to rotate the shaft. Clear now? So, power developed. So, power developed, that is also called shaft power. That means power developed by the turbine. Power developed by the turbine, it is your shaft power. What is called shaft power? and that is also called output power. That is also called output power, and this is equal to rho q. Rho q is the mass flow rate into change in velocity Vw1 minus Vw2 into the blade velocity u. That's it. This always you have to remember. That means this is what beta? This is your mass flow rate m dot. This is your mass flow rate m dot. This is your change in the whirl component velocity, and this is your blade velocity. Okay, this is your blade velocity. Put all this value. Density you have, yes or no? Density you have 10 to the power 3. Discharge, that means volume flow rate you have 5. Vw1 you have, see, Vw1 you have, Vw1 you have, where it is? Oh, so Vw1 you have, Vw1 is what? Vw1 we have to calculate or not? No. So Vw1 is what? Vw1 is equal to V1 minus U. Vw1 equal to V1 minus U. Somewhere we have to calculate, I think. Okay, no problem. Okay, no problem. So what is your Vw1? So this is your VR1. Okay, VR1. So Vw1 is what? Vw1. This is your same. Why? Because Vw1 is the horizontal component of this V1. Yes or not? So horizontal component of this V1. So what is your V1? V1 you have. So horizontal component of absolute velocity is Vw1. Okay. So the horizontal component itself, it is Vw1. So this is your Vw1. And this velocity, it is given how much? 40 meter per second. Why? Because this is a straight line. So Vw1 you have, Vw1 is 40 minus Vw2 you have 23.09 into the peripheral velocity 31.4 you have. So how much it is? How much it is, beta? It is your 2.65 megawatt. This is the power developed by this turbine. Now, in the question, if they are asking the efficiency, hydraulic efficiency or manometric efficiency of the turbine, what is the efficiency of the turbine? So, if you find turbine efficiency, also called hydraulic efficiency. This is your what, beta? Power developed by the rotor. Power developed by the turbine. Power developed by the turbine divided by the water power, या power available divided by the water power या available power या input power. So my dear, if you calculate, so we have power developed. What is the power developed? 2.65 cross 10 to the power 6 watt. Megawatt is there, so watt is there. What is the water power? Water power rho GQH. Yeah, rho QGH. Rho Q is the mass flow rate, m dot G into H. That means it is in the form of potential energy. What is the head? So this H is the head available. Available head. So if you have available head, that means rho is there, Q is there, G is there, but H in this case it is not there in this question. In this question it is not H is there. So where it is H? No, it is H. What is the head? If there is a head is available, so it may be have to solve the hydraulic efficiency. So here in this question, H is not given. So we cannot find the hydraulic efficiency. So if this is given, we have to find the efficiency. So like that, we have to find the efficiency of the turbine. So efficiency of the turbine is power developed by the turbine. Power developed by the turbine you have to calculate just now, and divided by water power. What is the water power? In the form of potential. That means if this is a turbine and there in the turbine, at the turbine, there is a water reservoir. So at what height the water is reserved, that is in the form of potential energy. So that is your water power. So if the head is there, at what level the water reservoir is there, so if you have the information, just divide with that what is the power developed, you have to efficiency. Clear? This is clear? Everyone please tell me. Now, so I hope you all are clear of this problem. So it may be asked in this form also. Now my dear, in this question, it may be like that. Okay, no problem. We'll have to check this. So we have to start with this problem. This is your also hydraulic problem, but it is this is your 2008. Why we have to discuss here? Why? Because this is in this year IISc Bangalore. This question is asked when the IISc Bangalore is. So this is important question. So intentionally we have to take. See this one. So water having density, it is given, leaving from the nozzle with a velocity of 10 meter per second. That means this is your V1 in swing from the nozzle. And the jet strike at the bucket. At which point it will strike? Splitter. Mounted on the Pelton wheel. So this is the Pelton wheel. The wheel is rotating. That means this is omega. It is given 110 radian per second. The mean diameter, that means diameter of the rotor, it is given. The jet is splitted. Yes, from the splitter, the jet is splitted, and the jet is splitted into two equal streams by the bucket. See, jet will split. Jet is splitted into two by the bucket, such that each stream is deflected as 120. That means the jet is in swing. Jet is striking at the splitter, and from the splitter, the jet will split into two parts, and the deflection it is the same at 120 degree. Previous question, the deflection it is 165. Here is 120. As shown in figure, the friction of the bucket is neglected. That means K you have to neglect. Magnitude of the torque exerted by the water on the wheel per unit mass flow rate, it is given. That means torque divided by rho Q. Mass, what is the mass flow rate? Rho into Q. Rho into Q. So torque divided by rho into Q, you have to find it. The option it is given. Okay. So what they are asking that if, so this is like that, beta. See this one. This figure, you have to see this one. What is that? See, there is the Pelton wheel. This is your velocity. And that velocity will be split on the blade at that splitter, and it will split into two parts. It will split into two parts. That means it will split into two parts. So how to develop this equation? To develop this equation, to develop this concept, same concept is there. What is that? See, beta. We have to design at this point, at this junction. Okay. Okay. So my dear, this is your in-swing jet. This is in-swing jet, okay, with a velocity, this velocity V. Now from this one, this is your, let's suppose it will go like that. Now, but there is a splitter is there, splitter, so it will split into two component. So it will split into two component. It will split into two component. One, it is in this direction. Other, so it is splitting, it is in a horizontal manner. This is not in a vertical, beta. This is in a horizontal. Please be careful. This is in horizontal manner. Thank you. This is your horizontal minor is there. So what is the angle it is there? This angle it is there, splitting angle. This angle is 120, same splitting is there. Same splitting is there, 120. Now my dear, one thing is very clear in the case of Pelton turbine. What is that? See, this is your splitter. See, this is your splitter. So what is the function? This splitter, let's suppose this splitter is a kind of knife. So the jet, let's suppose this jet is coming at a diameter, and this knife will cut this jet. This knife, splitter act as a knife. See, this splitter act as a knife. So this knife will cut this jet into two equal parts in this question. So, and that jet, once the jet is splitted into two equal parts, that will also move in the same plane as compared to the in-swing jet. That's why this is called tangential. So what is in from the radius distance, the same is out from the radial distance. So the blade velocity doesn't change at inlet and exit. Okay. So, so that this is your splitter. Now my dear, so this is your incoming jet and all the given, this is your deflected jet. So this is your deflected jet. This is your deflected jet and this is your incoming jet. This is your incoming jet. Now, so always we have to take, if you draw the velocity triangle, if you draw, this is the straight line, if you draw the velocity triangle, so you have to take this triangle, is a responsible triangle. Beta 2, let's suppose this is beta 2, deflected angle. What is the beta 2 beta? Total angle is 180 minus 120. It is how much? 60 degree. So in this case, there is a 60 degree is the angle. Now, what is given here? All the part, so this is clear. Now, we have to, so what is given here? Please, given. What is given? Given. Density given, 10 to the power 3. We have a data, don't worry, kg per meter cube. Velocity of jet in swing, 10 meter per second. And if this is there, so this rotor is try to rotate. This rotor is try to rotate. And that rotation, it is always also given 10 radian per second. What is the given? It is 10 radian per second. This is your 10 radian per second. This is your 10 radian per second of the rotation, it is given. Okay. So this is your 10 radian per second. Now, okay. So omega it is given 10 radian per second. Okay. Diameter of the wheel it is given, mean diameter, obviously. Why? Because bucket height is higher, so we have to take a mean diameter. So we have to find the exit torque. Torque exerted. Torque we have to find, and you have to find the torque in Newton meter per mass flow rate, that means kg per second. We have to find. Okay, what is this kg per second? This kg per second is nothing. It is your rho into q. Rho into q. Okay, and this is your force torque. Okay, now, so from this, if this velocity omega it is given, and if the radius it is given, so we have to find what is the peripheral velocity, yeah, rotor velocity. How much? Pi d, yeah, pi d n. N. So pi d n upon 60. So here n it is not given. So we have to take another formula. U equal to R into omega. So we are not able to find U blade velocity, rotor velocity from this one. Why? Because n RPM. So this is in RPM. Mind it. This is in RPM. pm, and this is your in radian per second. Radian per second. So what is the radius? D by 2 it is given, into omega it is given. Put all this value. So if you put this value, the 5 meter per second. That means this 5 meter per second is what? This 5 meter per second is the tangential velocity which is responsible to rotate the rotor. That means if this is your rotor, my dear, if this is your rotor, okay, this is your rotor. So this, if rotor is rotating like that, so this is your velocity. This is the velocity in this direction. So this is your velocity. Clear na? This is, it is visible? Yes. So in this direction, this is the velocity u. This is your u is there. So from u to here, this is the radius r. And this developed the torque to rotate this wheel, omega. Simple mechanics is there. Clear na? This is the simple mechanics. Okay. Now, so what is the power developed? We know that from the turbine, what is the power developed? Rho Q into 1 plus K cos beta 2 into V1 minus U into U. See, there are many methods to solve these questions. If you are, whether you use the formula or not, that is the very simple thing. Here is no any K it is given, loss is, there is no any loss, so K equal to 1. Put K equal to 1. Cos beta 2, you have beta 2. V1 you have, put the value. So power it is there. So what is the power? This is rho Q 1 plus cos beta 2 V1 minus U into U. Okay, my dear. Now we know that what is the power? Power is equal to torque into omega. So from here you can find easily the torque. What is the torque? So P is equal to torque into what is the omega? Omega is equal to U by R. So from here, if you find the torque, this PR by you cancel out. So it will convert into the torque formula, and the torque it is rho Q 1 plus cos beta 2 into V1 minus U into R in place of that one. Now, this is your mass flow rate, divide by this one. So, this torque divided by rho into Q, they are asking. So, what is that? 1 plus cos beta 2 into V1 minus U into R. Put all this value here. 1 plus cos 60 degree V1 jet velocity it is there 10, peripheral velocity 5, diameter it is given 1 by 2. If you calculate this one, this is 3.75 Newton meter per kg second. Clear? Simple problem is there, nothing else. There is a very simple problem. What is that, beta? What is the main thing is that in the question? The main thing is that how to, you know this formula or not? Yeah, you have to calculate also. So if you calculate for that one, there is an inlet velocity is not given. So directly if you have a knowledge about this formula, you cannot solve this problem. Why? Because in this case, there is no any concept of velocity triangle. It is not given that relative velocity. It is not given that any whirl velocity is not given. So if you beta 2 it is given, if you draw the velocity triangle, you can easily draw like that. If you draw that one, so we have to draw like that. No problem at all. No problem at all. How to draw? See this one very clear. No problem. What is that? See, this is what, beta? This is VR2, yes or not? This is VR2, relative velocity from the deflection. This is VR2, and same idea. This is VR2, and in this direction, this is VR2. So in this direction, there is a velocity u. This is your u velocity. So in this, at this line, this is the direction of u. At this line, this is the direction of u. Yes or not? Yes or not? This is the direction of u. Now, if you take this velocity, one second. If you take this velocity, this is the velocity of u. If you take this velocity, this is also velocity of u in this direction. So, which velocity you have to take? This velocity or this velocity? Please tell me. This velocity or this velocity? This is the line of action of this u velocity. We have to shift this line of action of this u velocity. So, which velocity you have to take? This one or this one? Please tell me. This velocity or this velocity? You don't take this velocity. Why? Because the u velocity and relative velocity are the same sense. U velocity and relative velocity are the same sense. So, ting, 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 this relative velocity, ting, 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 ting. So, these are the same sense. But if you take this one, ting, 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 this one, and if you take, this is our opposition. So, the actual velocity, this one. So, you don't select this velocity, okay? Now, what is the V? V are the opposite sense. V are the opposition. So, if you draw this diagram here, so this is the line of action of V. So, this U, V, R2, U is there. So, this is your V2. This is your V2 is there. This is your V2 is there. Now, at the inlet, there is a line diagram. So, this is your V1. This is your V1. At any point, this is your U. And this is your VR1. VR1. And in the Pelton turbine, what is the velocity of V1? The same is velocity of V2. VW1. Work component. VW1. Why? Because this is horizontal. So, what is the velocity of absolute velocity? The same as the work component. So, these are the same. Now, my dear, from here, you have to easily find this component. So, if you find this one, little bit. So, this is your V2. So, V2 component is this from, if you join this one, so this is your whirl component, that means this is your V2. VW2, this is your VF2. So, if you have, what is the power? Power you have, P is equal to rho Q VW1 minus VW2 into U. You have this one. So, but yes, beta 2 is there. You can easily find VW2. You can easily find VW2. What is the VW2? VW2 is V2 cos. So, VW2. So, VR2 cos beta 2 is total is there. VR2 cos beta 2 is total is there. Yes or not? This is what? This is what? VR2 cos beta 2 is there. This VR2 cos beta 2 minus U1 is equal to VW2. This VR2 cos beta 2. VR2 cos beta 2. This angle and this angle are same. This angle and this angle are same. So, this VR2 cos beta 2 is this one. Minus U you have. So, you can easily find VW2. What is V1? VW1? V1. Put this value. So, this is per unit mass. So, power per unit mass rho Q. So, you have VW1 minus VW2 into U. So, you have this one. Multiply with the, what is the torque? Torque is your power is equal to T into omega. So, you have this power per unit mass basis. Put this value. Divide this omega. You have to a torque. So, this is your torque. So, find this torque. Very easy, no problem. So, either you have to apply the standard formula, but this is your best rule. But this, when you have to apply this concept, when you have to strong in the velocity triangle. Yes or not? Yes or not? So, once you have a velocity triangle, you can easily find it. Otherwise, there is a problem in there. Clear? So, you find like that anyway. So, this is the question related to in 2008. Clear now? Now, yes, this is a very good problem, I am telling you. This is the question related to 2021. This is a very good problem. What is the problem is there? See this one. A vertical shaft. Yes. Same idea. Pelton turbine always remember like that. That means sometime interview they may ask you ki the line of action of the shaft. So for the Pelton turbine, the line of the shaft it is in a horizontal manner. Generally 99% the Francis turbine, the shaft is it in vertical mode. Number first. Number second, in the case of Pelton turbine, the very important thing is there. Throughout the pressure is constant. Why? Because in the casing there is atmospheric pressure. So what is the fluid is in and fluid is exit after passing from the bucket, the pressure at inlet is the same as the pressure exit, and that pressure is equal to the atmospheric pressure within the casing. But in this case it is not. Pressure and velocity, pressure energy and kinetic energy both are changing. Why? Because we have to have a losses in there, so we have to make a spiral casing so that energy will maintain at a constant at inlet to the wicket gate or a guide vane. Okay. So what is that? A vertical shaft of a Francis turbine rotate. So that means a rotation. This is a n RPM it is given. The available head. This is very important question is there. This is the very important. If you know the basic structure, basic component of the Francis turbine, then in that case you may have to solve. Otherwise, you cannot able to solve this problem. Okay. So what is that? Available head of the turbine at inlet is given. So this is what beta head. It is in the form of energy. We can also think that. That means energy. This is your water power. This is in the form of water power. What is water power? Water power is the nothing in the form of head. If you talk about in the form of head, the net head available at the entry of the turbine, that is called the water power. So the net head it is given, and that is in the form of rho GQH. So what is the head available at the inlet of the turbine? This is given. So H inlet, head available, H available inlet, it is given 200. And my dear, this head available inlet we have to also call water power. In the case of water power, what is the water power? Rho QGH. So this H is that one. Clear na? Okay. The tip is speed of the rotor. Tip is speed. Why? Because in the case of Francis turbine, the Francis turbine, see, someone asks you, what is the flow nature in the Francis turbine? See, the entry must be a radial, either in Kaplan turbine or Francis turbine. Entry must be in radial. Entry must be a radial. But whilst during the rotor, that means if you engage with the rotor, so throughout the rotor, it may be radial to axial. That means a mixing is there, or a radial, pure radial is there. That means, see my dear, let's suppose this is your entry. So let's suppose this is your shaft. Okay, this is shaft and this is your entry is there. So this is your entry, it is in radial direction. What is the direction? This is the direction of the shaft, and this is the radial direction, this is the axial direction, like that. Okay. So this is like that. Vertical shaft is there. Now this is your entry. So entry it is in perpendicular to the axis of shaft, that means radial. But whilst it is entry, it will try to deflect, and the deflection, the path of that stream, the path of that stream of the fluid is try to conversion in a radial to axial. So somehow that is called mixed flow. But what is the case of the Pelton Kaplan turbine? Radial entry is pure radial, but exit is pure axial. That means see like that. It is in here, and it is axial. That means it is there is no any gap, there is no any time span. That means there is no any possibility to rotate the stream while it is engaging in the rotor of the turbine. No, it is direct entry to the radial and directly converted into axial. So that Kaplan turbine is a pure axial turbine. But in the case of Francis turbine, entry must be a radial, In the both cases, either in the Kaplan turbine or either in the Francis turbine, in the both cases, entry must be radial. Entry must be radial, but axial in the case of, axial it is in the case of Kaplan turbine, that is called pure axial. But in the case of Francis turbine, there is not a pure axial. It will try to convert it into radial to axial, so that it is mixed. Clear? So the tip speed of the rotor, that means this is the rotor speed, tip speed of the rotor. Okay, so we have to calculate all the speed at the tip. So tip of the rotor speed is 40 meter per second. Water lifts the runner. Water lifts the runner. That means, see, and second thing also there, in the case of a reaction turbine, there must be, we have to installation of a draft tube, but in the case of the Pelton turbine, we are not bothering about the draft tube. Why it is happening, we already discussed in the class. So if you are, if you know this thing, then this is okay, otherwise there is a very difficulty in the situation. So in the case of a reaction turbine, we must use a draft tube. Without draft tube, we cannot handle the reaction turbine. But in the Pelton turbine, there is no use of the draft tube. So water lifts the runner. That means inlet to the draft tube. Draft tube always installed at exit of the turbine. Draft tube always installed at the exit of the turbine. That means eye of the turbine. Okay. That water lifts the runner of the turbine without whirl. See, my dear, without whirl. Without whirling component is there. That means the velocity at exit is 90 degree. Okay, the velocity, that means V2 must be perpendicular to the V1. That means V2, you may call the V2. V2 is the outlet velocity must be equal to the V2. That means there is no any whirling component. Whirling component, what is the whirling component? Who is the responsible to develop the whirl component? The responsible fellow is the component of a absolute velocity at the exit in the direction of blade velocity. Clear? So this without whirl, that means the velocity V2 must be perpendicular to the U2. Now, my dear, this is your reaction turbine. So in the reaction turbine, very important, I'm telling you. In the case of a Kaplan turbine, the flow is axial, not tangential. So what is the difference between axial flow and tangential flow? First tell me. In the case of the Pelton turbine, the flow is tangential. The flow is tangential. So the flow is tangential. That means in the place of Pelton turbine, the flow is tangential. So this is a tangential direction. So what is the in velocity distance is there? The same velocity at exit, that means V1 equal to V2, U1 equal to U2. But in the case of a Kaplan turbine, that means pure axial. In also, what is the velocity at inlet? There is a tip is there, so mean diameter you have to take. So at the mean diameter, what is the inlet velocity distance? Same as the exit velocity distance, but it is not like the tangential. Very confusing term. 90% student confuse here. Okay, sir, in that case, Pelton turbine also U1 equal to U2, and in the case of a Kaplan turbine also U1 equal to U2, but the mode are differ. In the case of the Pelton turbine, why? Because the tangential flow is there. But in the case of axial turbine, so let's suppose there is something is axial. So if this is your axis, so very simple thing. There is an axis is there. There is axis there. Something is axial. So what is the inlet at there? So let's suppose this is the axial flow. This is the flow, and this is the axis of the shaft, and this is the flow. So what is the distance at in? The same axial distance is out. So the radius doesn't change throughout the motion. Radius doesn't change throughout the motion. So what is the velocity of U1? The same velocity of U2 in the case of Kaplan turbine. But in the case of a Pelton turbine, the velocity is tangential. So what is radial distance at inlet? The same radius distance is outlet. Very careful in this case. Okay. So see, in the case of Pelton turbine, U1 equal to U2. In the case of a Kaplan turbine, U1 equal to U2. But the both are the mechanism wise differ. Matlab geometry wise differ. So in the case of Pelton turbine, tangential, due to the tangential flow, U1 equal to U2. In the case of a Kaplan turbine, due to the pure axial, U1 equal to U2. Clear? So the velocity at the exit of the draft tube, it is given. Now See, water lifts the runner of the turbine without whirl. That means there is no any whirling component is there. Velocity at the exit of the draft tube. This is the exit. Why? Because we have to draft tube install. So at the exit, that means final velocity at the exit of the draft tube 3.5 meter per second. The head loss in a different component of the turbine is there. This line is very important, I'm telling you. So there are different component in the case of Francis turbine. What is that? Stator, guide vane, rotor, draft tube. Major component. So a stator and guide vane. So first entry of the, what is the called turbine, beta? What is the turbine? In the case of a Pelton turbine, what is the turbine? Turbine is only rotor mounted with the blade. Nozzle is not a part of the turbine. But in the case of a Francis turbine or a Kaplan turbine, the turbine, it is the blade plus casing is also part of the turbine, and also there is a rotor. So what is that, beta? In the case of a Pelton reaction turbine, a Francis turbine, we cannot use the nozzle. A spiral casing acts as a nozzle. But in the case of a Pelton turbine, we must be add extra nozzle. That means there is an external part. But in the case of the reaction turbine, the part of the turbine is itself a nozzle that play a role of casing. Clear? So what is that? Stator and guide vane losses is there, rotor is there, losses, and draft tube is there. Same idea. Rotor have a more loss also there. This is the practical things there. Someone you ask you, in which component the losses are more? So the rotor, the losses are more. Then there is stator and guide vane. Then there is a draft tube. Decreasing order of the losses. So more losses at the rotor, less losses in the draft tube. In between these two, there is a losses in guide vane or stator. The flow rate through the turbine it is given. That is throughout the flow rate it is given. Hydraulic efficiency they are asking. Okay. So what is the hydraulic efficiency? Output by input. What is the output? Output, it is your shaft power. Input is your head available. That means inlet to the turbine. Now my dear, see this one. So see this one. So this is your reaction turbine. Okay. So what is that? See, this is a spiral casing is there. This is a spiral casing is there. Now the fluid is into the from the penstock. This is inlet form of the penstock. This is the penstock, and this penstock will be finally it is in the shape of the scroll casing or volute. That means spiral casing. So volute is the casing. It is in volute shape. So see this one. This casing, the area. See this one area. This area. This is your outer casing, outer volute part, and this is your outer. So see this one, and this is your rotor. This is rotor. So see this area, beta. The area, the wedge, the shape, wedge shape is there. See, continuously the area of the passage will continuously reduce so that the velocity is uniform in all this one. Why? Because there is a frictional loss. If the fluid is moving from this one, energy will lose. So who's maintain the energy? The shape of the spiral case maintain the energy. So that in the case of this one, we have to use the volute casing. Now this is your guide vane, also called stator. So this is your guide vane, which is which will control the flow rate. It will adjust it at this point. It will adjust at this point. So this is called guide vane. Now this is called runner blade. So these are all are the runner blade. Runner blade, runner blade, runner blade. These are the runner blade. So the guide vane will be guide vane. What is the purpose of the guide vane? The guide vane is the purpose to exactly there is no any jerk is there. So the angle of the exit of the guide vane should be match of the angle of the runner blade. So there is a smoothly will departure from the guide blade to the entry of the runner blade. There is a smooth. So that will also provide the direction of the flow. Okay. Also control of the flow. Will control of the flow. Okay. So see this one. These are the casing is there. These are the guide vanes. And these are the runner blade. So this runner blade and these are the shaft is there vertical. So what is that beta? In the guide vane there is pure radial direction in the runner, yes or not? This is pure radial. Now after that it will continuously circulating. It will continuously circulating, that means a rotating is there. So at the entry it will radial, and at the final exit it will pure axial. During that, this is the mix. That means it will try to rotate the fluid. That means it will in, then there is a rotation is there, and then there is exit. So there is a curvilinear nature. So sometime it is called a mixed flow, and there is a runner blade is there. So this is your runner blade is there. What happened? Yes, this is your runner blade is there. Okay, this is your runner blade is there. So this is runner blade. So losses different. So if the flow through the turbine is radial through the turbine, not entry, through the turbine, this is the flow through the turbine. If the flow through the radial or a mix of radial and axial flow, that is called Francis turbine, and this is the velocity triangle of the Francis turbine. So this is at inlet, my dear. This is your inlet. This is your V1 velocity, which is entry to the rotor. This is a rotor blade, beta. This is a rotor blade, and who will provide this velocity? The provider. So this scroll casing, this will act as a nozzle. This guide vane, the guide vane act as a nozzle in the case of reaction turbine. So this is V1 entry, this is V1, U1, this is VR1, like that. And this is a, in this one. So it is given like that. What is given in this case? In this case, the given it is like that, beta. See, the water lifts the runner of the turbine without whirl. So without whirling. So here, there, this is also called V2. So V2, it is in vertical direction. So in this one, there is no component in U direction. So if there is no component of V2 in a U direction, that means the whirl velocity at exit V2 is there. So if there is an inclination, with respect to U, less than or greater than 90 degree, in that case the whirl component will produce. But if it is 90 degree with the velocity of rotor velocity exit, there is no any whirl velocity. Clear na? There is no any whirl velocity. Clear. Now, so we have to try to solve this problem, and this problem is a very good problem is there. We have to try to cover up. I think today this is the last problem for the today, because the time is very. So we have to find. We have to find what to have to find? Hydraulic efficiency. Eta H. What is the eta H? Hydraulic efficiency, sometimes also called the manometric efficiency. Okay, that is your power developed by the rotor, shaft power. This is also called shaft power developed by rotor divided by power available from the fluid. This is also called hydraulic power. So what is this, beta? What is this? Power developed by the rotor. If you form in the form of H, this is H of power developed by the rotor. That means H of the turbine. Turbine power. So power developed by the turbine, that is called head developed by the turbine. And this is your available head. That means what is the power? That means at what height? This will directly depends upon the height of the reservoir. So this is your power available from the fluid. This is your inlet. So this is your H inlet. Okay. This is your power developed by the turbine. Sometimes this is called shaft power this is called shaft power, and this is called water power. Water power. Clear? Now, so water power, that means inlet. See this one, beta. Let's suppose this is your turbine, okay, and this is your draft tube, okay, and this is your inlet of the turbine, and this is your head at which the reservoir is there. So this is your H. So this is your inlet into the turbine, okay. This is at exit of the turbine. This is at draft tube, so it is exit at the draft tube. So these are 2 points. This is inlet to the turbine 1. This is exit from the turbine 2, and this is exit of the draft tube 3. Clear na? So 1 to 2 is the loss of stator, guide, and so there is a 3 losses is there. Yes or not? So there is 3 losses is there. Stator, guideway, and rotor. These 2 at in between 1 to 2. These 2 are stator or guideway and rotor. These are the turbine, within the turbine. So this is the head loss between 1 to 2. But in this case, draft tube, this is 2 to 3. Very important. So stator and guideway plus rotor, it is 1 to 2, and in the draft tube 2 to 3. Okay, and it is also given the exit velocity from the draft tube. That means there may be a losses at the exit from the draft tube. Okay, so 1 to 2, this is 1 and this is 2. So 1 to 2 is the losses in between guide vane, rotor, and stator vane, and 3 at the exit of the draft tube. Okay, and this is draft tube. So we have to take, this is at inlet. So H inlet is equal to what, beta? H of the turbine. H at inlet is equal to H of the turbine. Okay, plus stator plus guide vane. Stator plus guide vane plus H of the rotor, stator plus what? H of the rotor plus H of the draft tube plus exit velocity, very important, V3 by head 2g, V3 by 2g, V3, this is your V3 ka square, V3 ka square by 2g. Please be careful here. What I am telling you, total inlet is what? In the turbine. That means what is the turbine will develop. Okay, so this is at 2, very important. This is at 1, very important. This is at 2. This is your 1 to 2. This is your 1 to 2. This is your 2 to 3. 2 to 3. And this is at 3. Clear? Clear, yes or not? Please, yes or not? This is at 1. The 1 is total input. That total input is at a turbine output plus in between 1 to 2 plus 2 to 3 plus 3. So how to write? You may be right H1 to 2 plus 2, 2 to 3, 3. So we have to write H1 like that. H1 is equal to H1 to 2, H1 to 2 plus H at 2, 1 to 2, H 1 to 2, 2 to 3, 2 to 3. Yeah, you can say like that. Here space is less. 1 second. Okay, we have to take like that. See, H1 this H1 is equal to H1 to 2, okay, plus H2 plus H2 to 3 plus H3. This is very important thing. If you know this one, you can very easily handle the head related problem in the turbine. So this H is the inlet to the turbine. This 1 to 2 it is in during the turbine. So during the turbine the fluid will be contact with the rotor plus guide vane. H2 it is the exit from the turbine. 2 to 3 during the draft tube. 3 exit of the draft tube. Clear? So this include 1 to 2. This include 1 to 2. This include 1 to 2 is this one. Stator, guide vane, rotor. This is your stator plus guide vane plus rotor. That's it. This 2 is exit from the turbine. Exit turbine. This 2 to 3 in the draft tube. In the draft tube, and this 3 exit of the draft tube. Draft tube. Exit of the draft tube. Clear? This is your exit of the draft tube. Now, what is given here? What is given here? Given. What is given? H inlet. Inlet head, available head, it is given 200 meter. That means this is your turbine. This is your draft tube. This is your head, H is it is given. This total head H. Inlet it is given. This is at point 1. This is at point 2. This is at point 3. Okay. So it will move like that. Okay, into the draft tube. Okay. So it is given. Now, so H inlet, this is your H inlet 200 meter it is given. Okay, no problem at all. V3 it is given at this point. Exit velocity from the draft tube. How much it is given, beta? 3.5 meter per second. Clear? V2 exit from the draft tube. Exit from the turbine. It is given or not? Please see this. See the tip speed of the turbine rotor. Tip it is the exit. Tip it is not root. Tip exit. That means at this point, tip exit at this point it is given. Tip exit. Then it is move in the rotor. This is the part of the rotor. So tip exit. So tip exit is 2. Tip exit is 2. So tip exit is 2. So that means V2 it is given. How much it is given? 40 meter per second. Okay, 40 meter per second. Now, so H inlet is equal to H of the turbine. That means H inlet is equal to H of the turbine. Oh, see this one? H of the turbine. That means H2 turbine plus H1 to 2 during the rotor. Yeah, you can say that. H1 to 2 during the rotor plus H2 exit of the turbine plus H2 to 3 in the draft tube plus H3. Yes or not? Now, H inlet it is given. How much? 200. H1 to 2 stator plus guide vane. How much it is? Stator plus guide vane. 1 to 2 it is given. Stator plus guide vane. Stator plus guide vane 5. and plus rotor 10. So stator plus guide wing H2 to 3. So this is your stator plus guide wing, and this is given 5 plus 10. H2 is the turbine. So turbine it is given. Turbine it is given how much? The head available 200. The speed of the rotor this much. Okay. 2 at the draft tube. This is turbine exit. 2 it is given. 2 it is what? Turbine exit. Yeah, entry to the draft tube. This is 2 it is given. Now this is in the form of during the draft tube. So during the draft tube is what? It is head available in the draft tube 5, 10, 2. So this is 2. So entry to the draft tube. So during the draft tube it is not given in the loss form. Okay. So it is not given. What is the loss? It is not given. Not given. But the exit it is given. So this is your V3 square upon 2G. Okay. Put this value here. So H turbine. So 1 second. 1 second. 200. Okay. And this is your H of the turbine. Head developed. This is H of the turbine. Head of the turbine. Very important. And draft tube it is given. Not given, it is given. Draft tube it is given. So H of the turbine, it is, we have to find it. Plus this 1 to 2 during the rotor, 5 plus 10. This 5 plus, this is your 5 plus 10. This H of the turbine, plus in the draft tube, this is 2. Plus H3 is equal V3 square upon 2G. And this V3 square upon 2G is what? 3.5 the whole square. 3.5 the whole square divided by 2 cross 9.81. So if you calculate this one, you have to easily find H of the turbine, head developed by the turbine. You can find easily. So H developed by the turbine, if you calculate, this is your 182.375 meter. It is not negligible. Why? Because in this question it is given. Draft tube loss, it is given 2 meter. So don't ignore this one. Draft tube, this is a draft tube. So 2 to 3 it is in draft tube. It is in draft tube. Draft tube. Yes or no? So draft tube it is 2 it is given. Now it is exit. So H of the turbine we have to find it. So now put the value of this efficiency. So from here H of the turbine it is your 182.375 divided by H inlet 200. So how much it is? 91.87%. So I hope you like this session, and also this session will be more helpful those type of student who just start the fluid turbo machinery and also who finish the turbo machinery. So we have to take some question, and many more question is there, 2 to 3 question. If there is a time is available, another slot, we have to we damn sure that we have to discuss this one. Okay. Up to that, if you have any confusion in this one, please do the comment. I will resolve that comment very soon. Thank you.